All right, let's get started. Hello, everyone. Welcome. Thank you all for making it to my talk. Appreciate it. It's been a long couple of days, and it's been brilliant. I've met some really smart people. And I'd just like to thank the organizers, the sponsors, and the Moov team especially for putting together this amazing event, for giving me a chance to speak and meet all of you people. All right, let's get started. So I'm going to be talking about idempotency, ensuring idempotency, future-proofing your API with zero disruptions. So if you're a product person, engineer, director, working in any capacity in a fintech company, I hope you'll find something of value here. So just a brief introduction about myself. My name is Mustafa Ali, and I am a founding software engineer at Method Financial. For those of you who don't know what Method is essentially a financial platform. It is a unified API that allows you to connect with consumer liabilities, get real-time data, make payments, etc. So it helps other fintechs, banks, lenders to build on top of it using consumer liabilities. Prior to Method, I worked at Topple, which is a Web3 ESG-focused blockchain protocol. Over there, I led the development of their digital wallet application. And I worked on some product-facing and on-chain applications like their Block Explorer and some decentralized applications. So just a quick shout out to the engineering team at Method. They're the ones who inspired me to be here today. So these are just some pictures I put together from a recent offsite trip to Mexico City. If you haven't been there, 10 out of 10 would recommend. If you're planning an offsite soon, you should go there. So high-level agenda for today, we're going to be going over some key concepts around what idempotency means, walk through a couple of examples, and look at why it's important. Right? We're going to look at the overarching problem and see why we need idempotency in our APIs, and our solution at Method, and just some solution ideas in general, and then we'll conclude with some key takeaways. So idempotency, if you've been working with fintech APIs in if you've worked with the fintech APIs in a decent amount, you've probably come across the term and you're probably familiar with it. If not, it's essentially a concept in API design that ensures that the same operation can be safely repeated multiple times without causing unintended side effects, right? So that's an important concept, especially when you're working with sensitive endpoints like payments, transfers, charges, etc. So essentially, if you have duplicate requests coming in, the end state on your server stays the same. So nothing changes over there. So let's look at a couple of examples in API design. So if you're working with APIs, you're typically working with some kinds of resources, right? So let's say if you have a user resource, you're probably going to be fetching that resource. You're going to be making updates, deleting it, etc. And some of these HTTP methods are by definition idempotent, right? So if you try to retrieve, let's say, user123 multiple times, the end state on the server doesn't really change. If you delete it multiple times, the end state on the server doesn't change, right? So these HTTP methods are by definition idempotent, right? Other times you're trying to create a resource, right? So if you have like an account for a user, you send a post request with the user ID, with the merchant, etc., and then you create the resource. But you can imagine if you send that multiple times, even if it's the same request, that might get created twice, right? So it's not idempotent by default. Similarly, in financial transactions, if you're trying to make a payment, even if you're trying to make the same payment multiple times, it's not necessarily the case it's more than likely that payment is going to be processed twice, right? So it's not idempotent by definition. And so why does idempotency matter in general? Well, for one, as an API developer, you want to take steps to preempt any unwanted user actions, right? So regardless of whatever the case may be, you want to ensure idempotency in your APIs so that you prevent users from inadvertently triggering actions multiple times, protecting them from unintended outcomes, right? Secondly, it's also important for data integrity and consistency. Overall, if you have a distributed system, you want to make sure that all of your servers share the same view of what the state of the system looks like. It's also important that you share the same view with your clients as well. And then also mitigating financial risks. So repeated transactions due to non-idempotent requests, they can lead to unintended transfers, payments, or charges, and that's it can cause monetary losses. And then, given all those 3 points, overall, you can imagine it simplifies the engineering process, right? It's easy to debug issues when they're only happening once instead of a lot of times, right? And then in general, it enhances the user experience. So now that we have a basic grasp of what idempotency means, we've gone through a couple of examples, we've seen why it's important, let's talk about what the problem is. Well, a core issue is that API failures are inevitable. There's some failures that you don't really have control over, regardless of how good of an engineer you are, how many safeguards you have in place. There's some issues that are going to happen and you need to plan for them, right? So what are some reasons for those kinds of failures? Well, for one, there's network errors. So if you're working with APIs and you've ever seen something like an econ reset, econ aborted, those kinds of status codes, timeouts, lost connections, they can happen. They're out of your control. So you can try to plan around them. But these things can cause state inconsistencies and erroneous retries by the client, right? And then if you're developing an API, you're most likely going to be using third-party upstream dependencies, right? So you might have a dependency for making payments or getting financial data. And all of these third-party upstream APIs can throw transient errors, right? And those errors can cause your requests to fail halfway through. And then you can also have user interface glitches, right? So if you have a client that's consuming your API, their UI can have glitches, and then those can trigger duplicate requests. And then lastly, in a distributed environment, you might have system crashes or failovers that can cause request interruptions and basically cause the requests to fail halfway through. And given all of these failure scenarios, essentially from the perspective of the client, it's unclear whether the request should be retried or not, right? So it's also unclear whether the operation that they were trying to perform actually succeeded or not. So it leaves them, in a very weird state. Yeah, that's why I have that meme over there. So with that context in mind, if you lack idempotency in your APIs, what's going to happen, right? So you're going to have unintended consequences. Like we talked about, you're going to have some inconsistent state, inconsistent data that's being viewed by the client versus what's being seen on the server side. There's going to be a negative impact on the user experience. So it might lead to some confusion, frustration, and it might, depending on how many parties are involved, it might also increase the support overhead significantly. You might also be looking at financial repercussions, right? So refunds and reversals, and in some cases also irreversible transactions, like if you're dealing with crypto payments. So it's especially important in that context. And then overall, it also slows down the product development lifecycle, right? And it impedes the engineering process. Your engineering resources get diverted into solving all of these issues that come up. And then it's expensive context switching. So I have this snippet over here from this show, Silicon Valley, which I'm presuming some of you might have seen. There's a scene where the engineers are all flustered. They're freaking out, trying to figure out what's going on. All of their data is being erased. And essentially what's going on is one of their investors, who's a comical character, accidentally leaves the tequila bottle on the delete key. So it erases all of their data. But this doesn't have anything to do with idempotency, so it's kind of a stretched example. You might not be looking at this kind of a scenario, but in a real world scenario, you can imagine, if, for example, let's think of an example, you have a consumer-facing application, right, that's consuming your API, let's say the method API, and the method API allows you to make payments. And the user interface glitches out, maybe there's a bad deployment, and suddenly you're seeing multiple requests for the same action. And that's okay if it's happening once, but then multiply that by 100,000 times, that you're seeing at a lot of issues, right? So it might lead to something like this. So these are some actual real-world examples. What happens is you get upset customers, they go online, they express their frustration, and you get something like this, right? So for example, this is probably the most appropriate example over here, the Uber Eats one, which is basically the person is complaining that they were charged twice because of an app error that had the message internal server error, try again. And then what ended up happening is that they were charged twice for the same order, right? So that's something you don't want to see. And I can't 100% guarantee that these issues were caused by a lack of idempotency. But what I'm saying is if you didn't have idempotency, you'd be seeing the same kind of complaints, right? So there's an example from DoorDash, Stripe, Uber Eats, Cash App, all the apps that deal with payments. This was us when we came across this issue. And if this is you right now, then don't worry. You're not alone. You're in the right place. You're learning about what idempotency means, and we'll talk about what the solutions are over here. So let's talk about how do we get started implementing idempotency in our APIs. So let's try to make this a bit more interactive. Let's see, how many, if you're starting from scratch and you don't have any idempotency built in right now, but you have an existing code base, how many lines of code approximately do you think would it take to build an idempotency layer? Any guesses?
200,000.
20? Okay, good guess. I guess not off. Multiply that by 10, approximately 200 lines of code. So this is from our repo. We had 237 lines of code. And what we realized is it's not that deep, right? When you think about how do you want to build it, when you start writing down the requirements, you realize you don't need to rewrite your entire code base, right? So you can build around it. And these are some implementation guidelines that we had for ourselves, and I hope they can be useful for you if you're starting to think about your idempotency layer, right? So one, you want to make sure that you enable idempotency for all of your post endpoints, right? Because those are the ones that usually trigger some sort of action, trigger some sort of background processes. So you want to make sure that you enable idempotency for all of your posts, and even if you're dealing with patch, then maybe even that. But essentially, for anything that triggers an action that you want to make sure only happens once. And secondly, you want to keep things simple and effective. You don't want to modify the existing code base. We're huge fans of not touching what currently exists and writing around that. So there's that. And then you also want a way to store idempotent requests. So you can imagine if you're going to be returning the same response for the same duplicate requests, you want to store that response somewhere, right? So you want a global store for idempotent requests. And then guaranteeing exactly one semantics comes down to, again, the definition of idempotency. You want to make sure that it only happens once and only once. So there's that. And then principle of least astonishment, it's just a fancy way of saying you don't want to surprise your users. If someone is consuming your API and you implement idempotency, if an API endpoint is idempotent, then you want to make sure they're also seeing that, right? And then ensuring two-way idempotency, essentially what that is if you have idempotency built in on the server side, so an API call doesn't change the state of your server, you want to make sure the client sees the same picture. If they make duplicate requests, they shouldn't be seeing different responses. So you want to make sure you have two-way idempotency in that sense. And then another thing to think about is expiration or idempotency windows, meaning if I am going to make a duplicate request and I do want it to go through, then how do you plan around that? So the first step in the broad solution is something called an idempotency key, the safeguard in our digital world, ensuring every action counts, but only once. So idempotency keys, essentially what it is it's a unique identifier that you can attach to your HTTP requests, your transactions. Essentially for an action or a specific transaction, you can attach it, and then you can make sure that it only happens once, right? And then currently there's not exactly an existing standard out there. So if you go online, if you try to look at how it's implemented, you'll find that a lot of companies have built around it in different ways. For example, I have a few examples listed over here. So PayPal uses something called a PayPal request ID. Twilio has its own thing, and then X idempotency key, et cetera. There is, however, an existing RFC out there to make this a standard, so we can all follow the same patterns follow the same thing and have a better understanding, which is to use an idempotency key, just that, as an HTTP header. And that's also what we use at Method. It simplifies things. It's also intuitive. And then once you have an idempotency key, you can attach it with your HTTP requests, and you can make sure that you can be rest assured that one idempotency key equals one transaction, regardless of how many times you send that HTTP request. So what does the overall flow look like, right? Step one, the client generates a key. It's a unique idempotency key for a specific transaction that they're trying to make. They send the transaction along with the key to the server. The server grabs the key, looks in its global store of idempotent requests, checks if there's a match, and returns the cached response. Otherwise, it proxies the request to the backend servers, gets the request, gets the response, forwards it, and then caches it for future requests. Right? So pretty straightforward overall. And I have an example over there. We can see the idempotency key is attached as an HTTP header. And one thing to keep in mind over here is the generation of the key is actually kind of important, because you want to make sure that it's strictly tied to the operation that you're trying to make. It's also not something that's going to change frequently. So if it shouldn't be, for example, a random key that you don't keep track of. It shouldn't be the current timestamp, right? It's going to change in the next second. So it should be something, it could be a concatenation of the account that you're trying to make a payment with, and then maybe the current date, right? Something that wouldn't change and you can keep track of in your own database for the same action, right? So we've talked about the easy part, which is a key that the clients can use. You haven't made any changes to your server. So let's talk about how we can do that on our end without changing our existing code base, right? So what are some major requirements over there? One, we don't, again, like we talked about, we don't really want any code changes. So there should be minimal code changes. It shouldn't reflect, should not affect the user experience, right? So there shouldn't be any changes to the API responses that you currently have in your API. Overall, your idempotency layer should be fast, it should be reliable, consistent, all those good things. It should be distributed, should be just overall, those are just some good guidelines for any service you have. And when you start thinking about it, really what it boils down to, it's just you need a proxy so you can intercept and inspect all incoming requests. And then you need a cache where you can store all of your idempotency key with their associated responses, requests and responses that you can use for future duplicate requests, right? So this is our learning journey, which is we started by thinking about, hey, just cache it at the edge. And then we were like, oh, but what about using atomic transactions and then rollbacks and keeping track of the state of the request? And then we slowly made our way back down to just caching it at the edge, right? Because it's easy, it's simple, it works. So we took a look at some caching solutions at the edge. Hey, what could we use to put this thing in front of our servers at the edge? It can cache, it can intercept all the requests, and then it can cache them, return them for future requests. So we thought about, what about a Redis cache? I mean, it's a good idea, but when you have a small group of 3-4 engineers, it's a bit too much work and maintenance, and we don't want to deal with that at the moment. We have, we want to work on product development more than we want to work on maintaining a Redis cache. There's AWS Lambda at Edge, which is a really good option, but you have the same problems that you have with most serverless function services, which is they have the cold start problem. It's kind of complicated to set up, do testing, and it's not super turnkey, right? And then you have Cloudflare workers. Cloudflare workers, really easy to set up. There's no cold start problem. It takes 0 seconds to start up. And it's also super cost effective, especially for this problem, right? So more on why Cloudflare workers. Well, for one, especially if you're working with JavaScript, right? It's super easy to set up. They have native support for JavaScript, right? They use the V8 Chrome engine for starting all of their Cloudflare workers. That's also why there's no cold start problem, because V8 engine is really fast and it just spins up a JS isolate, and then everything just works. right? And since it sits on the edge, there's reduced load on your servers, right? You're not dealing with spam requests. You're not dealing with duplicate requests. They're cached, and the responses can be returned by the Cloudflare worker. They also have a host of other services like their key value store, durable objects that you can leverage for this specific problem. And then again, since they're on the edge, it's a global edge network. Cloudflare has a huge global edge network, right? So there's super low latency. And then we have a screenshot from our own production dashboard, and you can see over there that it takes sub 1 ms, and dealing with a lot of requests, about 1 million requests and 3 million sub requests, and it's super fast. No errors, 100% success rate. So how do you get up and running quickly in 4 steps? Well, step 1, you create a Cloudflare worker application. This is an actual screenshot from our own application, item production. You can guess what item stands for. You set up routing for your requests, so you want to intercept all incoming requests at a specific URL, so you add that for your Cloudflare workers to intercept that. And then you write a few lines of code, right? So these are the 200 lines of code that we were talking about before. Essentially, how a Cloudflare worker works is if you've ever done web development, you probably came across service workers, right? So they have this concept of implementing a fetch method to intercept any incoming requests. So Cloudflare workers follow the same sort of pattern where you essentially have this fetch method that you need to implement to perform any sort of logic, modify requests, or do any changes at the edge over there. So you implement the fetch event handler to intercept incoming requests, and for post requests with the idempotency key header, you check the cache to see if there's any cached responses from before, and then you replay them if it already exists. Otherwise, you forward the request and cache the responses for future requests, right? So that is a screenshot from our actual production code base. What we have over there is I can walk through just the definition of the functions. We have that main fetch function that I just talked about, which essentially the request comes in. You check if you can call the should bypass item function to see if it's a post request, if it has the idempotency key, do all of those checks, and if it does, then you can check the idempotency cache and you can call replayed response to return the response. Otherwise, you can bypass the worker, call the services, and then do all of that again. Cache the response, and the next time it comes in, you'll just return the cache response.
Quick question on that. Is that kind of working like middleware, like in your back end, where it's picking up requests and able to do this functionality?
Sorry, say that again?
Like middleware kind of picking up the requests that are coming in on the server side?
Exactly.
Okay.
Exactly. So the question was, is it kind of acting like a middleware that's picking up requests? That's exactly right. So it's sitting at the edge in front of all of our servers. It's inspecting all the incoming requests, checking if it's, okay, this is a post request, it has an idempotency key. Let me first check the cache to see if there's any stored responses. If there is a response associated with that idempotency key, then just return it. Otherwise, forward that request, right? So it's super useful in that context.
Do you force your clients to have an idempotency key, or do you just let it on through if they don't give you one? I'm just curious.
That is right. So that burden falls on the client. Your responsibility is to, one, ensure that if something is idempotent, you let them know, right? You need to pass in an idempotency key. So that burden does fall on the client. Yeah. And then step 4, you're done, right? You test it, and same screenshot as before. You pass in an idempotency key, and you can do it multiple times, and you'll get back the same result, essentially. So that, in a nutshell, is what idempotency was, right? So let's go over some key takeaways. For one, API failures are inevitable, right? So you're always going to see network issues, transient errors, and you want to plan around that, right? So taking an idempotent-first approach is crucial. It's crucial for maintaining data integrity and consistency, and for building resilient, dependable, and future-proof APIs. You're always going to have to make API design trade-offs like you were talking about. It's not something entirely that you can control, right? It's something that also the client has to adhere to. So, and then secondly, there's also maybe, for example, you have a bad deployment and your code throws a 400. Somebody made an idempotent request. Now that's cached. If they do it with the same key, even if you fix the issue, they're going to see the same thing, right? So it's a design trade-off that you have to make. And in general, idempotency is not just about avoiding duplicate operations. It's about building a reliable, trustworthy, and compliant financial system. You want to make sure that you build a good reputation with all of your clients, with all of your customers. So it's important in that context. And lastly, you can, like we talked about, you can build your idempotency layer in less than 200 lines of code, right? Sorry.
How do you ensure false positive or false negative the way you look at it? Like this reply request should have been entertained, but because of cache, the reply that was a duplicate request, they don't take an action. So something downstream timed out, but the cache is not updated. Okay, this API request has failed. Then let the reply go. How do you manage that?
So if I'm understanding correctly, you're saying, what if the cache is not up to date? You're saying if there's a race condition?
Or if it's a panic, right? This reply was the genuine reply request. It should have gone through. But because it was cached, we reply that, oh, this is a duplicate request. I'm not going to take an action.
Right. So I guess I'll say two things to that. One is you're only going to cache after you receive the response, right? So that's one thing. If you receive an incoming request, if you don't find anything in your cache, you proxy it, get the actual result, and then you cache it, right? So that's one thing. And then the other thing I'll talk about is one thing I think you were kind of hinting at is race conditions, right? So what if you have multiple requests coming in for the same thing, and both of them go through before the first one got cached? That's especially where Cloudflare workers come in. I can go back and talk about these durable objects. Durable objects are super cool in that context where they can prevent these kinds of race conditions, where they're basically kind of persisted classes that you can instantiate, for example, in this case with an idempotency key. And there's only one instance of them alive at a time. So until that instance of the class has been resolved, right? So if that request has been processed, any duplicate request with the same idempotency key would be held back until that entire process completes, right? So if there's a race condition, if you trigger multiple requests at the same time with the same idempotency key, it would have to wait for the first one to succeed before it can continue on with the next one. And by the time it gets to the next one, the cache would already exist with the replayed response. Right? Yeah, so you can build your idempotency layer in less than 200 lines of code. Before we finish, I'd like to leave you all with this quote by Phil Carlton, who is a computer scientist, very well-respected computer scientist. He said, there are only two hard things in computer science: cache invalidation and naming things. The reason I like this quote is, it's a good quote, but there's an even better one by Matthias Reis. There are only two hard problems in distributed system: exactly once delivery, guaranteed order of messages, and exactly once delivery, right? So that's it for my talk, and I'll leave the floor open for any questions if you all have any. Yeah.
So is the idempotency key generation purely flag-based?
Yes,
Okay.
that would be.
Does your middle layer do any checks for identical content of a request?
That's one thing you can add on if you want, more sort of guardrails around that entire concept. But essentially, I think that's like a trade-off that you have to make. Do you want to have that checks? If you are going to have those checks, then you need to be clear about that, right? The thing with that is, ideally, you don't want to have that, right? Because you want to give the control of the idempotency to the client. If they're already generating a key, then you don't need to be checking the request itself. If you were going to be checking the requests itself, then you're taking the control away from them and doing the checks yourself.
It really depends, right? Just if you manage the client, then sure, maybe. But if you have a completely public API that accepts balance transfers, for example, then that becomes a little more touchy.
That is true. So I guess in that context, then what you can do is you can be clear about what the idempotency key window is, right? So if there's an expiration date over there, that's extremely useful to have if you're going to be checking the request body itself for duplicates. So I think that becomes more important in that context.
Okay, thanks.
Yep.
So besides the AWS Lambda Edge cold start problem, what are the limitations that you observe using AWS Lambda?
I'll be honest with you, we were kind of biased for using Cloudflare because our CEO was going to work there, and we already had everything set up over there. So all of our routing, DNS was already set up on Cloudflare, so it was super easy to just spin up Cloudflare workers and get everything up and ready. We did explore AWS at Edge. The issue with that was it was kind of hard to test locally, right? So it wasn't as easy as a Cloudflare worker would be, and it's also, we were already familiar with the concept of service workers, so it's just already intuitive as to how it's going to work, and especially with the context of the thing that the other person was talking about, how do you deal with race conditions? That's much easier dealt with in Cloudflare workers with concepts like durable objects, as opposed to building your own thing around it in AWS at Edge. Yeah.
If you ever consider using it right now that they've already addressed the cold start problems with Lambda, yeah. So if you ever consider, consider using it.
Okay, that's good to know. Yes.
If you were starting, I guess, a greenfield, development, would you recommend using a separate caching layer or building idempotency into your, APIs? And I'll get to one by. I think this solution probably was a bit of a hole because usually your application is going to have some sort of a transactional unit which is going to commit. And by doing this caching in front, you could end up in situations where something does commit, but the response never comes back through the cache, and you allow duplicates.
Right. Sorry, could you repeat that? Because I can.
So I guess the question is, if you're starting from scratch, do you think, would you go with that? I get the feeling you added this layer onto existing application.
Exactly.
But if you already were just starting from a brand new application, would it be better to build this into your actual application's logic in the inbox as opposed to using a separate layer?
Right. So the question is, if you're starting from scratch, would you rather have something like this that wraps around your existing code base, or would you rather build it inside your APIs, right? So I'm assuming you're talking about, you mentioned transactions, right? So we have some upstream dependencies, and maybe the request fails after, so maybe it charges the user, and then after that it fails, right? So depending on that context, right? So I would say if you have the engineering resources, it might be worth it to do that because you have the time to build around atomic, rollbacks, transactions, all of those kinds of things. You can build around, but you can build that inside your APIs, and I think that's probably a better user experience, as long as you're conveying a consistent response to the user, right? You can keep track of the state of the request, where it failed, and then pick that up later with the same idempotency key. So you can build around that, but it's really complicated because, as far as we explored it, it was going to be a huge rewrite. So this presents a much more of a reasonable middle ground where you're caching the responses regardless of wherever it failed, and then just replaying them if you see the same idempotency key. And the trade-off that we're making is if there's something that could have been fixed, it could be resolved in a customer support query instead, right? That's kind of a trade-off that we make.
There's a narrow window, and you can still get one of those nasty emails.
Exactly. Yeah. Any other questions at all? No? All right. Thank you.